Let's look at phase equilibrium. We start with intermolecular forces, which is abbreviated as IMFs. This is intra. Okay, so intermolecular forces, these are attractive forces between molecules. Okay, then intramolecular forces, these are attractive forces holding an individual molecule together. For example, in the hydrogen molecule, you can see these two atoms are held by covalent bond. Also in the chlorine molecule. Then types of intermolecular forces. Number one, we have the London dispersion forces. London dispersion forces are present in all molecules, especially non-polar molecules. They are caused by temporary fluctuations caused by temporary fluctuations in electron distribution. They are generally the weakest intermolecular force. Okay, for example, oxygen molecules are attracting each other. Okay, so there there's some London forces being experienced. Okay, the second type of intermolecular attraction is dipole force. Okay, so this occur in polar molecules. This occurs in polar molecules. Okay, so it results from the attraction from the positive end of one molecule and the negative end of the other. Okay, so these molecules have a dipole moment. Okay, they have a dipole moment. For example, in hydrogen chloride. Okay, we know that chlorine is partial negative, then hydrogen is partial positive. So this molecule has a dipole moment. Okay, so the higher the electronegativity, the more polar the bond is. Okay, so in these compounds, there are forces. There is what we call dipole interactions. Okay, so in this case, the chlorine atom is more electronegative than the hydrogen atom, so it pulls more electrons to itself. Okay, electronegativity is defined as the ability of an atom to attract shared electrons to itself. So we have a situation like this: partial positive, partial negative. So this will interact with another molecule in this way. Okay, so here there will be an attraction, so we can also have another here, partial negative, partial positive. There will be dipole here. Okay, so here partial positive, partial negative. So dipole will be experienced here, also here. Okay, so these are what we call dipole interactions. Okay, so dipole interactions are stronger than London dispersion forces. Okay, so these are stronger. So dipole is stronger than than London dispersion forces. Okay, so we can look at another type. So another type of a force that we are going to look at is hydrogen bonding. So let's look at hydrogen bonding. So number 3 is hydrogen bonding. Hydrogen bonding. Okay, so hydrogen bonding is a special type. This one is a special type of dipole force. It's a special type of dipole force. Okay, occurs when hydrogen is bonded. When hydrogen is bonded to nitrogen, oxygen, or fluorine. Okay, occurs when nitrogen, oxygen, or when hydrogen is bonded to nitrogen, oxygen, or fluorine, and is attached to nitrogen, oxygen, or fluorine in another molecule. Okay, so e.g. water. Okay, in water there is hydrogen bond. Okay, so it is given a special name, hydrogen bond. It is given a special name, hydrogen bonding, because compounds containing these bonds, compounds containing these bonds are important in biological systems. Okay, they are important. For example, a good example is water. Okay, so the energy of hydrogen bond, depends on the electronegativity. Depends on the electronegativity of X atom. So for example, fluorine is more electronegative than oxygen. Oxygen more electronegative than nitrogen. Nitrogen more electronegative than chlorine. Okay, so what we mean X atom, so it means when hydrogen, X atom, so X could be this fluorine, oxygen, or nitrogen, or chlorine. Okay, so this is partial positive, then this is partial negative. Okay, so it means this bond, the one that is formed between hydrogen and fluorine, is way much stronger than one formed between hydrogen and chlorine, because fluorine is the most electronegative atom. Okay, so let's look at another type. Another type is ion dipole. Ion dipole force or attraction. Ion dipole force. Okay, so occurs between an ion and a polar molecule. This one occurs between an ion and a polar molecule. Between an ion and a polar molecule. Okay, so it is experience, or it is formed when an ionic compound dissolves in water. dissolves in water. For example, sodium chloride can dissolve in water, will dissolve in water to form sodium ions and chloride ions. Okay, so the attraction that forms between sodium ions and water, attraction forms between sodium ions and water, and H2O, water, okay, or water molecules. That's what we call the ion-dipole interaction. Okay, then we can now look at the order. What is the order of intermolecular forces, order of intermolecular force strength, So we have mentioned that the London dispersion forces, they are the weakest. So London dispersion, then followed by dipole, then followed by hydrogen bonding, then followed by ion dipole. Okay, so this is the order of intermolecular forces. So the strongest is the ion dipole. Okay, then we look at the effects of strong intermolecular forces. So what are some of the effects when a molecule has a strong intermolecular force? So number one, it's a high boiling point, melting point. Okay, can also experience high viscosity, lower vapor pressure, and also lower volatility. Okay, so these are some of the effects of strong intermolecular forces. Okay, so these factors determine how strongly molecules attract one another in liquids and solids. Okay, so let's look at properties of liquids. Okay, properties of liquids. So we start with surface tension. Okay, so surface tension is defined as the minimum energy required to expand the surface. Minimum energy required to expand the surface of a liquid, to expand the surface area of a liquid. Minimum energy required to expand the surface area of a liquid. That is surface tension. Okay, so the surface of a liquid behaves the surface of a liquid behaves like a stretched membrane. The surface of a liquid behaves like a stretched membrane due to intermolecular forces. That is why you are able to see some insects walking on water. Okay, this is because of this stretched membrane formed. Okay, so the other property of liquid is viscosity. Okay, so liquids resist to flow. Liquids resist to flow. So this resistance is what we call viscosity. This resistance is what we call viscosity. Okay, so the liquid's resistance to flow is called viscosity. E.g., honey is honey is more viscous than water, or honey has a higher viscosity. Honey is more viscous than water. Okay, or honey has a higher viscosity than water. Okay, then viscosity is temperature dependent. Viscosity is temperature dependent. Okay, so the lower the temperature, the higher the viscosity, and vice versa. Okay, then we can also look at the other property is the capillary action. Number 3, capillary action. Okay, so liquids can rise or fall. Liquids can rise or fall in a narrow tube. Liquids can rise or fall in narrow tubes due to adhesive and cohesive or cohesive forces. Okay, due to adhesive and cohesive forces. Okay, then the other one is evaporation or vaporization. Okay, evaporation. So molecules at the surface can escape into the vapor phase at temperatures below the boiling point. Okay, so here molecules can escape into the vapor phase, into the vapor phase at temperatures below the boiling point. Okay, then number 5, boiling point. A liquid boils when its vapor pressure equals the external pressure. So liquid boils when its vapor pressure equals 1 atm, 1 atmosphere. Okay, so that is the external atmosphere. Okay, so this is what we call normal boiling point. Okay, so when the vapor pressure of a liquid equals 1 atmosphere, that is normal boiling point. When it equals 1 bar, that is what we call standard. This is called the standard boiling point. Okay, but at this point we shall consider normal boiling point. Okay, so we shall concentrate much on the normal boiling point. So normal boiling point occurs at 180 m, which is equal to 762, which is equal to 760 millimeters of mercury. Okay, that is normal boiling point. Then the other property of liquid is fluidity. Fluidity. Okay, so liquids can flow because their particles. Liquids can flow because their particles can move past one another. Liquids can flow because their particles can move past one another. Okay, that is fluidity. Liquids can flow because their particles can move past one another. Then another property of liquids is no definite shape. We know the liquids take the shape of the container in which they are placed. Okay, so that's about properties of liquids. Okay, so now we can look at phase. So let's look at phase diagrams. Okay, so a phase diagram is a graphical representation of temperature pressure. Okay, so we are going to look at diagrams that represents temperature and pressure. Okay, so graphical representation of pressure temperature relationships. Okay, pressure temperature relationships. So a phase diagram has 3 lines. The phase diagram has 3 lines or boundaries. These lines we can call them phase boundaries. Okay, phase boundaries. So points of line corresponds to temperature and pressure. Points of lines corresponds to temperature and pressure. Points of lines corresponds to temperature and pressure at which phase equilibria can exist can exist between phases. Okay, so now we shall look at the phase diagram. So let's look at the phase diagram of water. Phase diagram of water. Phase diagram of water. So we shall draw the phase diagram of water. Okay, so this is the phase diagram of water. Okay, so on the x-axis we have temperature in degrees Celsius. Then on the y-axis, that is pressure in atm. Okay, so we can have 1 atm there. Okay, 1 atm. Then the 3 lines or boundaries, so we have one here. Okay, this is a point. Then this line goes like this, then another one goes like that. Okay, so this is just a sketch. So let's label A, B, D, C. Okay, so these are the three lines. So this is our solid, liquid, then gas. Okay, then at 1 atm, we can extend this line from 1 atm. So I have a point there which extend again there, then it comes down there. Okay, so we can put 100 there, then down from here, let's put our 0. Okay, so there's a lot of information that we can get from this phase diagram. So let's start with line AB. So line AB, okay, line AB, as you can see, it's from solid to gas. Okay, so line AB is a vapor curve for solid. Okay, line AB, this one is vapor curve for solid. Okay, so in this case we mean the ice. Okay, the ice, solid is the ice in this case. So line gives the temperature pressure points at which ice and vapor coexist. Okay, line gives temperature pressure at which ice and vapor coexist. Okay, so ice and vapor coexist. So this is a sublimation line. It's a sublimation line. So line AB is a sublimation line. Okay, so A to B, that is sublimation. Then B to A, that is deposition. Okay, like gas to solid, deposition. Okay, then we go to line BD. Okay, so line BD is a vapor curve for liquid water. Vapor curve. It's a vapor curve for liquid water. Vapor curve for liquid water. BD, vapor curve for liquid water. that is boiling point line, or from liquid to gas, that is vaporization line. Okay, boiling point line or vaporization line. Okay, so liquid and vapor, liquid vapor are able to coexist. Liquid vapor are able to coexist. Okay, so note at 100 degrees, the vapor pressure is equal to 1 atmosphere. Remember, we mentioned earlier that when the vapor pressure equals 1 atmosphere, that is normal boiling point. So this is normal boiling point occurs at 100 degrees for water. Then here, this is a normal freezing point. Normal freezing point. Okay, so the normal freezing point of water is at 0 degrees, or normal melting point. Okay, then the three lines intersect at point B. The three lines intersect at point B. You can see all the three lines intersect at point B. Okay, so the three lines all intersect at point B. So point B is called the triple point. Okay, triple point. Point B is called the triple point. Okay, so at triple point, ice, liquid water, and ice, liquid water, and water vapor. Ice, liquid water, and water vapor. Ice, liquid water, and water vapor coexist in equilibrium. Okay, then the temperature at the triple point is designated T3. The temperature at the triple point is designated T3. Okay, then the line which starts at B, terminates at D. The line which starts at B terminates at D. Okay, D is called the critical point. D is called the critical point. Okay, critical point. The temperature at the critical point is called is designated as TC, critical temperature. Then the pressure at the critical point is the critical pressure. Okay, so TC is the temperature. TC is the temperature above which vapor of the gas cannot be liquefied. cannot be liquefied. Vapor of the gas cannot be liquefied no matter how much pressure, is increased. Okay, that is the TC, critical temperature, is a temperature above which vapor of the gas cannot be liquefied no matter how much pressure is increased. Then PC, that is critical pressure. Critical pressure is a pressure above which supercritical fluid forms. Pressure above which supercritical fluid forms. So it means gas and liquid coexist at equilibrium. Okay, so above the critical point, 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 liquid and gas become indistinguishable. Liquid and gas become indistinguishable. Liquid and gas become indistinguishable. Okay, so that is what we call supercritical fluid. Supercritical fluid. Okay, supercritical fluid. Okay, then what is the significance? What is the significance of this phase diagram of water? Significance. What is its significance? Okay, so the phase diagram explains melting, freezing, boiling, sublimation, and condensation. Okay, and condensation. It also helps to produce the state of water. Also helps to produce the state of water at different temperatures. Helps to produce the state of water at different temperatures and pressure. Okay, helps to produce the state of water at different temperatures and pressure. Okay, so we can now look at the phase diagram of carbon dioxide. Okay, let's look at phase diagram of CO2. Phase diagram of CO2. Okay, so we need to draw the phase diagram of CO2. We shall compare it to that of water. So we have temperature, then pressure. Okay, so for CO2, we have 5.11 there. Then 1.0 is somewhere there, pressure. Okay, then we have 78 degrees Celsius there. Okay, then it goes like this. Okay, so this is the triple point. Okay, it looks like this. Okay, then the other point that we didn't mention for the first diagram of water is the position. It's the position of the solid liquid. The position of the solid liquid line. It has a negative slope. Okay, for water, the one that we just drew. Okay, take note that line BC has a negative slope. Okay, that is for water. It has a negative slope. So this is because the ice, solid water or ice is less dense than liquid water. Okay, ice is less dense than liquid water, therefore ice floats in liquid water. But for carbon dioxide, this is the opposite, the reverse of water. Okay, so here the solid liquid line has a positive. The solid liquid line has a positive slope, and solid carbon dioxide is denser than liquid carbon dioxide. This is the reverse of water. That is the reverse of water. So the only special thing about this first diagram is the position of the triple point. So you can see here the triple point for carbon dioxide is way above 1 atmosphere. Okay, is way above 1 atmosphere. So the triple point occurs at 5.11 atmospheres. But for water the triple point is below 1 atm. For carbon dioxide is well above the atmospheric pressure. So it is impossible to get any liquid carbon dioxide at pressures less than at pressures less than 5.11 atmospheres. So you cannot get liquid carbon dioxide at pressures less than 5.11 atmospheres. Okay, so that means that at 1 atm carbon dioxide carbon dioxide is sublime. It undergoes sublimation at 1 atm. Okay, at 1 atm. So it will undergo sublimation at 1 atm at a temperature, you can see here, at a temperature of negative 78 degrees Celsius. Okay, so at 1 atm CO2 sublime at a temperature of negative 78 degrees Celsius. So this is the reason why solid carbon dioxide is called dry ice. This is the reason why solid carbon dioxide is called dry ice. Okay, so you cannot get liquid carbon dioxide under normal conditions, only in the solid or the vapor. Okay, So, what are some of the applications of this carbon dioxide, okay, or phase diagram of this? So, in a fire extinguisher, carbon dioxide exists as a liquid. So, in a fire extinguisher, carbon dioxide exists as a liquid at 25 degrees Celsius under high pressure. Okay, so when we release carbon dioxide into the atmosphere at 180 m, the liquid changes to vapor. Okay, so at 180 m, liquid changes to vapor. And carbon dioxide is heavier than air, and its vapor now will extinguish the fire by keeping oxygen away. Okay, so now we can now look at let's now look at Clausius-Clapeyron equation. Clausius-Clapeyron equation. So Clausius-Clapeyron equation is given by the formula P2P1 is equal to delta H vaporization over R, then 1 over T1 minus 1 over T2. Okay, this is Clausius-Clapeyron equation. Okay, so where P1 and P2 are vapor pressures at T1 and T2 respectively. Okay, also take note that T2 is greater than T1, P2 is greater than P1. Okay, then delta H, that is molar enthalpy of vaporization. Okay, with units joules per mole. Okay, T is Kelvin temperature. Okay, then we know this is the natural logarithm. Okay, so this Clapeyron equation can be written in many different forms. Okay, so there are about 5 forms which we can write different. We can even put it when this thing here comes here, then if we interchange the temperatures, we start with T2 comes here, then T1 goes there, then we introduce a negative here. Okay, so if P1 on top, P2 down the way it is, then there will be negative. Okay, so it is important just to stick to one equation that you are used with than to know a lot. Then you may start now confusing the equation. So this is the equation that we shall adopt, and this one, it's easy to remember. Okay, it's the one you use in chemical kinetics for activation. If you want to calculate the activation energy, so you simply replace here, there's EA here, then K2, K1. So it's easy to remember. It's the same equation. Okay, so you can adopt this one. Okay, so let's have an example. Then, what are some of the applications of Clausius-Clapeyron equation? What are some of the applications? So this equation can help us to calculate vapor pressure, vapor pressure at a new temperature. Calculating vapor pressure at a new temperature, it can also help us determine the enthalpy. Determine the enthalpy of vaporization. Okay, and also studying phase changes. It can also help us to study the phase changes such as evaporation and condensation. Okay, so quickly let's look at an example. Okay, so calculate delta H. Calculate delta H for ethanol. Calculate delta H for ethanol. Given vapor pressure. Given vapor pressure at 40 degrees Celsius is 150 torr. The normal boiling point for ethanol. The normal boiling point for ethanol is 78 degrees Celsius. Okay, so let's calculate delta H. Solution. Okay, so first of all, identify T1 and T2, P1, P2. Okay, so we know that T1 is equal to 40 degrees Celsius. So we need to convert 40 to kelvins. Okay, so which will give us 313 K. Okay, then T2, as we can see, is 78 degrees Celsius. Okay, which when we convert, we add 273. Okay, convert that into Kelvin, so we have 351 K. Okay, so P1 is equal to 150 torr. Then T2, so we get T2 from the normal boiling point. So we know normal boiling point occurs at 1 atm, which is 760 torr. Then you apply the equation. Okay, we apply the equation. So ln P2 P1 is equal to delta H over R, 1 over T1, 1 over T2. So R is a gas constant. Okay, R is a gas constant, 8.314 joules per mole per Kelvin. Okay, that's the R. So now you substitute in the equation. So we have ln P2 760, 150. So we assume the units have cancelled. Then delta H, R, 8.314, 1 over T1. Okay, so here B, you can put the units so that you see how the units will be cancelling. Then T1 313 minus T2 351 K. Okay, so deal with the brackets, what you have in the brackets first. Okay, so you can also divide this side. So when you divide you are going to have ln 5. Okay, so delta H over R joules per mole per Kelvin. So here 1 over this, 1 over this, then you subtract. You are going to have 0.000034449. Okay, then you find it in 5, then you cross multiply. Okay, so here ln 5 you find, which will give us 1.6094. Then you cross multiply. So your delta H is equal to 39 kilojoules per mole. Okay, so that is how we can use this equation. Okay, so we can use it to calculate vapor pressure. We can also use it to calculate temperature when these others are known. Okay, so we can also do another example, but this one maybe you can solve it on your own. So chloroform has a vapor pressure, chloroform has a vapor pressure of 197 millimeters of mercury at 30 degrees Celsius, and 561 millimeters of mercury. Okay, and 561 millimeters of mercury at 72 degrees Celsius. Okay, so estimate its heat of vaporization, and normal boiling point. Okay, so this is the equation. This is the question that you need to solve on your own. Okay, so just a hint. Okay, so make sure we use the equation in P2 P1 is equal to delta H R 1 over T1 1 over T2. Okay, so take note that at normal boiling point occurs at 760 millimeters of mercury. Okay, so that will be your P2 when calculating the new pressure. Okay, so you are going to try this one. Okay, so we can end here. Then the next topic that we shall look at is properties of solutions. Thank you.